Welcome to my channel. Today we're going to discuss the evolution of generative AI, from early encoder-decoder models all the way to modern GPT and beyond. This journey will help you understand how we arrived at today's powerful language models and what the future holds. Generative AI refers to artificial intelligence systems that can create new content. Whether it's writing text, generating images, or even producing code, these models have transformed how we interact with technology. The key to understanding modern AI is tracing its architectural evolution through several major breakthroughs. We'll explore 5 critical milestones: the encoder-decoder foundation, the attention mechanism, the transformer revolution, GPT's decoder-only approach, and finally, where we're headed next. Each of these innovations built upon the previous one, solving fundamental limitations and unlocking new capabilities. Let's start with the encoder-decoder architecture, which became the foundation for sequence-to-sequence models around 2014. This architecture was revolutionary because it could transform one sequence into another, like translating "Hello World" from English to French as "Bonjour Monde." Here's how it works. The encoder reads the entire input sequence and compresses all that information into a single fixed-size vector called the context vector. Think of it like trying to summarize an entire book into one sentence. The decoder then takes this compressed representation and generates the output sequence, one token at a time. For example, if you're translating a sentence, the encoder processes all the English words, creates this context vector, and then the decoder uses it to produce the French translation. But here's the critical problem. No matter how long your input is, whether it's 3 words or 300 words, everything has to be squeezed into that same fixed-size context vector. This is the bottleneck. Imagine trying to fit all the details of a long article into a single tweet. You're going to lose information. For short sequences, this worked reasonably well, but for longer inputs, the model simply couldn't capture all the necessary information in that single vector. This limitation became the driving force behind the next major innovation. The attention mechanism, developed between 2015 and 2017, solved the bottleneck problem we just discussed. Instead of forcing the decoder to rely on a single compressed vector, attention allows it to look back at all the encoder's hidden states. Think of it like this. When you're translating a sentence, you don't just remember a vague summary of the input. You can actually refer back to specific words whenever you need them. That's exactly what attention does. The decoder can now attend to different parts of the input sequence with varying degrees of focus. Some encoder states might be highly relevant for generating the current output token, while others are less important. The model learns to compute attention weights that determine how much focus to place on each encoder state. A higher weight means more attention, a lower weight means less. This is why we call it a soft spotlight. Imagine you're on a stage with multiple actors, and you have a spotlight that can illuminate different actors with varying brightness. You might shine it brightly on one actor while keeping others dimly lit, but everyone remains visible. The attention mechanism works the same way, dynamically adjusting which parts of the input to focus on as it generates each output token. This breakthrough allowed models to handle much longer sequences effectively because the decoder could always access the full input context, not just a compressed summary. In 2017, the transformer architecture revolutionized the field with a paper titled "Attention is All You Need." The transformer introduced 2 major innovations that changed everything. First, it uses self-attention, which means tokens can attend to other tokens within the same sequence. Unlike the encoder-decoder attention we just discussed, where the decoder attends to encoder states, self-attention allows every token to look at every other token in its own sequence. This helps the model understand relationships and dependencies within the input itself. Second, the transformer completely eliminated recurrence. Previous models processed sequences one token at a time, sequentially. The transformer processes all tokens in parallel, making it dramatically faster to train. The architecture consists of two main components, an encoder stack and a decoder stack. Each encoder layer contains self-attention followed by a feed-forward network. The decoder layers have an additional cross-attention mechanism that attends to the encoder's output. One of the most important innovations is multi-head attention. Instead of computing attention once, the model runs multiple attention operations in parallel, each called a head. Different heads can learn to focus on different aspects of the relationships between tokens. One head might capture syntactic patterns, another might focus on semantic meaning, and another might track positional relationships. By combining information from all these heads, the model builds a much richer understanding of the input. The transformer became the foundation for virtually all modern large language models, and its impact cannot be overstated. GPT, which stands for Generative Pre-trained Transformer, simplified the transformer architecture by using only the decoder. This is called a decoder-only architecture. The key innovation here is the focus on autoregressive generation, which means predicting the next token based only on the tokens that came before it. To enforce this, GPT uses something called a causal mask. The causal mask ensures that when the model is processing a token, it can only attend to previous tokens, never future ones. Think of it like reading a book. You can only know what you've read so far, not what's coming next. This creates a triangular attention pattern. When processing the first token, the model can only see that first token. When processing the second token, it can see tokens 1 and 2. When processing the third token, it can see tokens 1, 2, and 3, and so on. The model never peeks ahead. This autoregressive approach is perfect for text generation. You give the model a prompt, and it predicts the next word. Then it adds that word to the prompt and predicts the next word again. This process continues, generating text one token at a time. For example, if you start with the cat, the model might predict sat, then down, building the sentence incrementally. What really set GPT apart was scale. GPT-1 had 117 million parameters. GPT-2 scaled up to 1.5 billion. GPT-3 jumped to 175 billion parameters, and GPT-4 is estimated to have around 1.7 trillion parameters. This exponential growth in model size, combined with massive amounts of training data, enabled GPT models to develop increasingly sophisticated language understanding and generation capabilities. Now let's look at what's coming next in the evolution of generative AI. GPT laid an incredible foundation, but researchers are pushing the boundaries in several exciting directions. First, we have multimodal models. While GPT focuses on text, models like GPT-4V and Google's Gemini can process and generate multiple types of content: text, images, audio, and video. GPT-4V added vision capabilities to GPT-4, allowing it to understand and reason about images. Gemini was designed from the ground up to be natively multimodal, meaning it doesn't just bolt on image understanding as an afterthought, it's fundamentally built to handle multiple modalities seamlessly. Second, there's the mixture of experts approach, or MOE. Instead of activating the entire model for every input, MOE architectures use multiple specialized subnetworks called experts. For each input, the model routes it to only a subset of these experts. This allows models to scale to enormous sizes while keeping computational costs manageable during inference. You get the benefits of a huge model without paying the full computational price every time. Third, we're seeing a focus on efficient models. Not everyone needs a trillion-parameter model. Researchers are developing smaller, highly optimized models like Microsoft's Phi and Google's Gemma that achieve impressive performance despite having far fewer parameters. These models focus on training efficiency, better data quality, and architectural optimizations to punch above their weight class. Finally, there's agentic AI. This goes beyond simple text generation. Agentic AI systems can plan, reason, use tools, and take actions to accomplish complex goals. They can break down a task, figure out what steps are needed, execute those steps, and adapt based on feedback. This represents a shift from passive language models to autonomous agents that can actually get things done. We will be getting into all those topics in detail. If you found this video helpful, please like and subscribe to the channel for more AI engineering content. Thanks for watching.